December 3rd, 1942. The sun hadn't yet cleared the Oakland Hills when Constance Bowman stepped through the gates of Moore Dry Dock Company in Richmond, California. The air tasted of salt water and ozone, that distinctive metallic tang that comes from thousands of welding torches burning simultaneously. She'd been a schoolteacher just 8 months earlier, correcting grammar assignments and planning history lessons. Now she carried a leather welding helmet under one arm and wore steel-toed boots that still hadn't quite broken in. The shipyard sprawled before her like an industrial cathedral, 7 parallel building ways lined with skeletal steel frameworks that would become cargo vessels. Overhead cranes moved with surprising grace, lifting prefabricated hull sections weighing 40 tons as if they were children's toys. The noise was extraordinary. Pneumatic hammers rattled against steel, cutting torches hissed, welding arcs crackled and popped. Foremen shouted instructions that barely carried over the mechanical symphony, and somewhere in that chaos, hidden among the orthodox welding procedures and approved maritime specifications, was a technique that would transform American shipbuilding, but remained officially forbidden by every standard the Maritime Commission had published. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Bowman wasn't looking for revolution that morning. She was simply trying to survive her shift without getting injured, without making mistakes that would embarrass her in front of the men who still resented women in the shipyards, without proving the skeptics right who said females couldn't handle industrial work. What she would witness instead was a quiet rebellion taking place on the third deck of Hull 473, where a welder named William Francis was doing something that could get him fired. He was welding downhill. The controversy seems absurd in hindsight. Welding downhill means running the electrode from top to bottom, letting gravity assist the molten metal's flow. Welding uphill means fighting gravity, dragging the electrode upward, while the molten pool tries to sag downward. Every welding textbook published before 1942, every Maritime Commission specification, every naval architecture standard insisted that structural welds must be executed uphill. The reasoning seemed sound. Uphill welding produced deeper penetration into the base metal, creating stronger bonds. The weld bead was thicker, more robust. Inspectors could see that an uphill weld looked substantial, reassuring. Downhill welding produced thinner beads with less obvious penetration. It looked, to traditional eyes, inadequate, weak, dangerous. But William Francis had learned to weld in the oil fields of eastern Texas, where pipeline construction operated under different rules than maritime work. Pipeline welders needed speed above all else. Miles of pipe needed joining in months, not years. The oilfield veterans had perfected downhill welding techniques that produced strong joints in half the time of uphill methods. When Francis arrived at Moore Dry Dock in September 1942, recruited from the Texas oil fields, along with dozens of other experienced welders, he brought those techniques with him, and he discovered they were forbidden. The Liberty ship program existed in a state of permanent crisis by late 1942. Henry Kaiser's revolutionary assembly line approaches had reduced construction time from 8 months to 6 weeks. The Richmond shipyards alone were launching 3 complete cargo vessels weekly. Newsreels celebrated this industrial miracle. President Roosevelt praised the shipyard workers as warriors on the home front. Admiral Emory Land, chairman of the United States Maritime Commission, publicly declared that American maritime production would bury Maritime Commission Storm, the German U-boat threat under sheer tonnage. But behind the propaganda, serious problems were emerging. The ships were launching on schedule, but quality inspectors were finding alarming numbers of defective welds. Cracks appeared in hull plates shortly after construction. Bulkhead seams failed pressure tests. Gun mounts separated from deck reinforcements. Some failures were catastrophic. The SS Schenectady, built at Kaiser's Portland Yard, broke completely in half while tied peacefully to a pier in January 1943. Investigation revealed that residual stresses from improper welding had combined with cold weather to fracture the hull like porcelain. The Maritime Commission responded with increasingly stringent inspection requirements and rigid enforcement of orthodox welding procedures. Every structural weld had to be executed uphill, using specific electrode types at precise amperage settings, following sequences approved by naval architects who'd never actually held welding torches themselves. The regulations made sense from an engineering perspective. Ships were critical war assets. Sailors' lives depended on structural integrity. There was no room for experimentation or shortcuts. If uphill welding was the proven method, then uphill welding would be mandatory. Anyone caught using unapproved techniques would be terminated immediately. William Francis understood the stakes. He also understood that the Maritime Commission's orthodox procedures were creating the very problems they were meant to prevent. Uphill welding, done correctly by a skilled craftsman with unlimited time, produced excellent results. But Liberty ship construction didn't allow unlimited time. Welders worked in cramped positions, often overhead or in awkward angles where maintaining proper uphill technique was nearly impossible. The thick weld beads that looked so reassuring to inspectors actually trapped more residual stress in the joint. The deeper penetration that seemed like a strength benefit often meant excessive heat input that warped surrounding metal, and the speed, or rather lack of speed, meant welders rushed their work, making errors that inspection caught later, requiring expensive repairs that delayed production. Francis had watched his fellow welders struggling with vertical seams on bulkheads, fighting to maintain uphill progression on welds that ran 8 feet from deck to overhead. He'd seen them produce thick, uneven beads that looked acceptable but contained internal flaws. He'd watched quality inspectors reject those welds, requiring them to be ground out and redone, wasting hours. And he'd known that downhill technique, the forbidden method from the oil fields, could produce stronger welds in less than half the time. The opportunity came on Hull 473, a Liberty ship designated for completion by December 12th. The vessel was behind schedule. A particularly complex bulkhead assembly in the forward cargo hold required 68 vertical seam welds, each one running between 6 and 9 feet. The approved procedure specified uphill welding using E6010 electrodes at 90 to 110 amperes. Estimated time for completion was 72 worker hours spread across 6 welders over 3 shifts. Francis looked at those seams and saw something different. He saw straight vertical lines with good access from multiple angles, perfect conditions for downhill welding if anyone had the courage to try it. He made his decision on the night shift when supervisors were spread thin across 7 building ways and inspection was less intensive. Francis selected his electrode carefully, not the standard E6010 specified for uphill work, but an E6013 electrode designed for fast fill applications. He set his welding machine to 135 amperes, significantly higher than the approved range. Then, instead of starting at the bottom of the seam and working upward as regulations required, he positioned his electrode at the top and began moving downward. The difference was immediate and dramatic. The higher amperage and downward progression created a fluid weld pool that flowed smoothly, gravity assisting rather than fighting the metal's natural behavior. The electrode moved at nearly twice the speed of uphill welding while maintaining consistent penetration. The weld bead emerged thinner than traditional uphill welds, but perfectly uniform without the uneven build-up that characterized rushed uphill work. Francis completed the first seam in 18 minutes. The approved uphill procedure called for 45 minutes minimum. He moved to the second seam, then the third, working with a rhythm and confidence that came from hundreds of pipeline welds, executed exactly this way. By the time the shift ended at 6 a.m., Francis had completed 42 of the 68 required seams. Working alone, he'd accomplished in 8 hours what the approved procedure estimated would take 6 welders 72 hours. The welds looked different from standard work, thinner, smoother, almost too neat. When day shift inspection arrived, they would either recognize superior craftsmanship or flag every joint as defective and potentially dangerous. Constance Bowman had been assigned to the same cargo hold that morning, working on electrical conduit installation near the bulkheads Francis had welded overnight. She noticed the seams immediately. They didn't look like typical Liberty ship welds. She also noticed William Francis returning to the hold after the shift change, still in his welding gear, watching from a distance as the quality inspector named Robert Marchant began his examination. Marchant was a 30-year veteran of maritime construction, trained in traditional shipyards where craftsmanship meant following established procedures without deviation. He approached the first weld Francis had completed and immediately frowned. The bead was too thin. It didn't match the thick, reassuring appearance of properly executed uphill welding. He marked the weld with yellow chalk, the notation indicating questionable quality requiring secondary inspection. He moved to the second seam, then the third, his frown deepening. Every weld showed the same characteristics: uniform thickness, smooth surface, minimal spatter. But wrong. Definitely wrong according to every standard he'd learned. Marchant completed his initial inspection and returned to the first seam with his testing equipment. He applied magnetic particle inspection, coating the weld with iron powder and applying an electromagnetic field that would reveal microscopic cracks invisible to the naked eye. The powder is distributed evenly, no indication of cracks. He tried ultrasonic testing, using sound waves to detect internal flaws or voids in the weld. The readout showed complete penetration with no voids. He performed dye penetrant testing, applying colored dye that would seep into any surface defects. The dye revealed nothing. Technically, the welds passed every objective test, but they didn't look right. Marchant marked his clipboard with a notation that would bring these seams to the attention of his supervisor and likely trigger an investigation into which welder had produced them using what appeared to be unapproved techniques. Francis watched this inspection process from across the cargo hold, knowing his experiment was about to have consequences. What he didn't know was that his forbidden downhill welds would trigger a confrontation between practical experience and institutional authority that would reshape Liberty ship construction, but only after months of conflict that nearly ended the technique before it could prove itself. The investigation began that afternoon when Marchant's supervisor, a man named Theodore Palmer, arrived at Hull 473 to examine the questionable welds personally. Palmer had worked for the Maritime Commission since 1938, helping to develop the very specifications that governed Liberty ship construction. He brought with him 2 additional inspectors and a metallurgist from the Commission's San Francisco office. They spent 3 hours examining Francis's work, running every test in their arsenal. The results were consistent and frustrating. The welds passed every objective measure of quality. Penetration was adequate. Strength exceeded requirements. Internal structure showed no flaws. But the technique that produced these results was nowhere in the approved procedures manual. Palmer ordered Francis to report to the yard superintendent's office the following morning. The summons carried obvious implications. Using unapproved welding methods on critical structural components was grounds for immediate termination and potential blacklisting from all Maritime Commission contracts. William Francis arrived at the administration building at 8 a.m. on December 5th, expecting to be fired. Instead, he found himself facing an interrogation. Theodore Palmer sat behind the superintendent's desk, flanked by the yard's chief engineer and quality control manager. They wanted to know exactly what Francis had done, what electrodes he'd used, what amperage settings, what specific technique. They wanted to know where he'd learned this method and why he thought he could ignore approved specifications. Francis explained the oil field pipeline welding background. He described how downhill technique, executed properly with appropriate electrodes and settings, produced faster, stronger joints than uphill methods under certain conditions. He acknowledged that he'd violated approved procedures but argued that the results justified the deviation. Palmer listened without expression, taking detailed notes. When Francis finished, Palmer asked a single question that revealed the core of the institutional dilemma. If your welds are superior to approved methods, why isn't downhill in welding part of our specifications? Francis had a simple answer. Because the people who write specifications never welded pipelines in Texas oil fields. They learned maritime welding in traditional shipyards where time didn't matter and uphill was always safer. But we're not building ships the traditional way anymore. We're building them in 6 weeks instead of 8 months. The old techniques don't work at this speed. We need methods designed for the conditions we're actually working under, not the conditions that existed 20 years ago. The confrontation highlighted a fundamental tension in the Liberty ship program. Henry Kaiser had revolutionized ship construction by abandoning maritime tradition and applying manufacturing principles from other industries. His prefabrication approach, modular assembly, and rapid worker training all contradicted conventional shipbuilding wisdom. Yet the actual welding procedures remained locked in orthodox methods developed for traditional construction. Kaiser had transformed everything except the fundamental act of joining steel, and that conservative holdout was creating bottlenecks that slowed production and ironically compromised quality as welders rushed to meet impossible schedules using techniques designed for leisurely craftsmanship. Palmer faced an impossible choice. If he accepted Francis's unapproved technique, he would be setting a precedent that workers could ignore specifications whenever they believed they had better methods. The entire quality control system depended on consistent adherence to approved procedures. But if he rejected demonstrably superior welds simply because they didn't follow the rulebook, he would be putting institutional authority ahead of actual performance. The Liberty ship program existed to win a war, not to validate maritime tradition. Palmer made a decision that was both pragmatic and bureaucratically cautious. He wouldn't fire Francis, but he also wouldn't approve downhill welding for general use. Instead, he ordered a comprehensive testing program. Francis would weld test samples using his downhill technique alongside samples welded using approved uphill methods. Those samples would undergo destructive testing, stress analysis, fatigue testing, and metallurgical examination. If downhill welding proved superior under controlled conditions, the Maritime Commission might consider revising specifications. Until then, Francis was suspended pending the outcome of these tests. The testing program began on December 8 at the Commission's Materials Laboratory in Alameda. Francis welded 20 test samples using his downhill technique with E6013 electrodes at 135 amperes. 20 additional samples were welded by experienced maritime craftsmen using approved uphill methods with E6010 electrodes at 95 amperes. The samples went to the laboratory's destructive testing facility, where they would be pulled apart, bent until they failed, subjected to repeated stress cycles, and examined under microscopes. The results would take 3 weeks to complete, 3 weeks during which Francis couldn't work and Hull 473's bulkhead installation fell behind schedule using orthodox welding methods. Constance Bowman watched this drama unfold with the fascination of someone who'd stumbled into a historical moment without quite understanding its significance. She continued her electrical work on Hull 473, but she paid attention to the welders around her. She noticed that several of the oil field veterans, the men recruited from Texas and Oklahoma who'd learned their trade in pipeline construction, were modifying their techniques in subtle ways. They couldn't use full downhill welding without risking Francis's fate, but they incorporated elements of his approach. Slightly higher amperage, faster electrode progression, techniques that split the difference between approved uphill methods and forbidden downhill approaches. The testing results arrived on December 28, 1942. Francis's downhill welds had outperformed approved uphill welds in almost every measurable category. Tensile strength was equivalent, meaning both techniques produced joints as strong as the base metal, but penetration consistency was superior in downhill samples, with less variation between welds. Residual stress, measured through X-ray diffraction, was significantly lower in downhill welds. The thinner weld beads that had looked inadequate to Theodore Palmer's experienced eye actually distributed stress more evenly than thick uphill beads. Fatigue resistance, tested by repeatedly stressing the joints until they failed, was 23% higher in downhill samples. Most importantly, the time required to produce downhill welds was 58% less than uphill methods. The metallurgist's report concluded with a recommendation that sent shockwaves through the Maritime Commission's engineering department. Downhill welding using E6013 electrodes at elevated amperage should be approved for vertical seam applications, where access permits proper technique execution. The method produces superior results in significantly less time. Continued prohibition of this technique represents adherence to tradition rather than pursuit of optimal performance. Theodore Palmer forwarded these results to the Maritime Commission's headquarters in Washington with his own notation. Test results confirm that an unapproved technique produces better welds faster than our current specifications. Recommend immediate revision of welding standards to incorporate proven improvements. Palmer's recommendation triggered bureaucratic processes that would take months to complete. Specifications couldn't simply be changed based on one testing program. Multiple shipyards would need to validate the results. Training materials would require updating. Inspectors would need instruction in identifying proper downhill technique. The entire quality control system built around uphill welding would need restructuring. While committees debated and procedures were drafted, William Francis returned to work at Moore Dry Dock in early January 1943 with unofficial permission to use downhill technique on specific applications. His welds continued to pass inspection. His productivity remained approximately double that of welders using approved uphill methods. And gradually, quietly, other oilfield veterans at Richmond shipyards began incorporating more aggressive downhill approaches into their work. The techniques spread through informal networks, welder to welder, without official approval, but with tacit acceptance from supervisors who recognized that production schedules mattered more than procedural orthodoxy. By March 1943, approximately 200 welders across Kaiser's 7 shipyards were using variations of downhill technique. The Maritime Commission knew this was happening. Quality inspectors documented the non-standard methods in their reports. But the welds passed testing, the ships were launching on schedule, and the alternative was forcing welders back to slower uphill methods that would cripple production. The Commission found itself in the awkward position of having rules on the books that everyone knew were being systematically violated, but no one wanted to enforce because enforcement would harm the war effort. The formal authorization came in stages, each one representing a small bureaucratic surrender to practical reality. In April 1943, the Maritime Commission issued Technical Bulletin 17-43, which acknowledged that alternative welding progressions may be utilized on vertical seams under controlled conditions with appropriate electrode selection and qualified welder certification. Vague, providing enough flexibility for shipyards to use downhill technique without explicitly endorsing it. The bulletin represented a compromise between engineering conservatism and industrial necessity. Downhill welding wasn't officially approved, but it wasn't forbidden anymore either. The real transformation occurred in the training programs. By summer 1943, Kaiser's welding schools were teaching both uphill and downhill techniques, though instructors carefully emphasized that downhill was supplementary and application-specific rather than a replacement for orthodox methods. New welders learned that vertical seams with good access could be welded downhill for speed, while overhead positions and restricted access still required uphill progression. The distinction seemed like semantic hair-splitting, but it allowed the Maritime Commission to maintain that they hadn't abandoned proven standards while simultaneously incorporating the faster techniques that production schedules demanded. The impact on construction time was measurable and dramatic. Hull 473, the vessel where William Francis had first demonstrated forbidden technique, was completed and launched on January 9, 1943, finishing 37 days after keel laying despite the investigation delays. Subsequent Liberty ships at Moore Dry Dock incorporated downhill welding from the start of construction. Hull 484 required only 28 days from keel to launch. Hull 491 took 24 days. The time savings came primarily from welding efficiency. Tasks that had required multiple shifts using uphill technique were completed in single shifts using downhill methods. The cumulative effect across thousands of welds per ship reduced total construction time by approximately 15 to 20%. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. More significant than raw speed was the improvement in weld quality. The paradox confounded maritime traditionalists but made perfect sense to anyone who understood human performance under pressure. Uphill welding demanded intense concentration and precise technique maintenance over extended periods. Welders working overtime shifts, exhausted and rushing to meet quotas, made mistakes. They used incorrect electrode angles, moved too fast through sections that needed slower progression, or overheated the metal, trying to force speed from a technique that wasn't designed for it. Those errors produced the defects that quality inspectors caught, requiring expensive repairs. Downhill welding, being inherently faster, reduced the pressure. Welders could maintain proper technique because proper technique didn't require fighting gravity while maintaining impossible precision over 45-minute weld runs. The method worked with human limitations rather than demanding superhuman consistency. By October 1943, statistical analysis of weld defect rates across Kaiser's 7 shipyards revealed a pattern that the Maritime Commission could no longer ignore. Yards that had most aggressively adopted downhill technique showed rejection rates of approximately 4.2% of completed welds. Yards, still primarily using orthodox uphill methods, showed rejection rates of 7.8%. The forbidden technique wasn't just faster, it produced fewer defects that required repair. The ships were being built better as well as quicker. The number of women welders incorporating these techniques added another dimension to the story. By late 1943, women comprised approximately 27% of Richmond's welding workforce. Many had been teachers, secretaries, or homemakers before the war. They had no preconceptions about how welding should be done, no attachment to maritime tradition, no ego investment in uphill methods they'd spent years mastering. When instructors showed them downhill technique and explained it was faster and easier in specific applications, they simply used it. The women welders became, statistically, the fastest adopters of the new methods precisely because they had nothing to unlearn. Constance Bowman, who'd witnessed William Francis's original rebellion, eventually transferred from electrical work to welding herself in March 1943. She learned both uphill and downhill techniques in the training program, but found downhill significantly easier to master. Her training records, preserved in the Kaiser Permanente Medical Care Program archives at the Bancroft Library, show she achieved certification in vertical downhill welding after just 11 days of instruction. The equivalent uphill certification typically required 3 weeks. Bowman would later write in her memoir, published in 1946, that downhill welding felt natural in a way uphill never did. "You worked with gravity instead of fighting it," she wrote. "The metal wanted to flow downward. Our job was to guide that flow, not to force it backward against its nature." Once I understood that principle, welding became almost meditative. The torch, the metal, and gravity all worked together instead of against each other. The technique's acceptance accelerated after the Liberty ship structural failure crisis of winter 1943-44. The SS Schenectady's catastrophic hull fracture in January had been followed by similar failures on the SS Esso Manhattan in March and the SS John P. Gaines in April. Investigation revealed that residual stress from welding was a contributing factor. The thick weld beads produced by uphill technique trapped more internal stress than the thinner, more uniform beads from downhill methods. This wasn't theoretical anymore. Ships were breaking apart, and the approved welding techniques were part of the problem. The Maritime Commission's response included a comprehensive stress analysis of different welding approaches. Engineers at the Massachusetts Institute of Technology conducted finite element analysis, a cutting-edge computational technique, modeling stress distribution in various weld geometries. Their report, published in June 1944 and declassified in 1958, concluded that downhill welds, with their thinner profiles and more uniform heat input, produced approximately 31% less residual stress than equivalent uphill welds. The Commission could no longer maintain that downhill was merely alternative or supplementary. The evidence showed it was superior for specific applications, and those applications comprised approximately 60% of the welds in a typical Liberty ship. Technical Bulletin 23-44 issued in July 1944, finally provided explicit approval for downhill welding. The bulletin specified electrode types, amperage ranges, joint preparations, and welder certification requirements. It mandated that all welding instructors teach downhill technique as a primary method, not an alternative. And it acknowledged, in language remarkable for its candor, that earlier prohibitions had been based on tradition rather than engineering analysis. The Commission's willingness to admit error represented a significant institutional evolution. Maritime authorities had spent centuries perfecting shipbuilding standards. Acknowledging that an oil-field pipeline welder had been right while they'd been wrong required humility that bureaucracies rarely demonstrate. The practical impact extended far beyond Liberty ship construction. Victory ships, the improved design that entered production in 1944, incorporated downhill welding specifications from initial design stages. The vessels were engineered with joints optimized for downhill technique rather than forcing downhill methods into designs created for uphill welding. Two tankers, built in, massive numbers for fuel transport, used predominantly downhill welding on their vertical tank bulkheads. The technique that William Francis had risked his job to demonstrate in December 1942 became standard practice across American maritime construction within 18 months. The statistical evidence of transformation was overwhelming. In 1942, before downhill welding gained acceptance, American shipyards produced 2,400 Liberty ships with an average construction time of 51 days and a weld rejection rate of approximately 7.4%. In 1944, with downhill technique fully incorporated, yards produced 2,700 Liberty and Victory ships with average construction time of 39 days and weld rejection rate of 4.1%. The ships were being built faster and better simultaneously, refuting the traditional assumption that speed and quality were inherently opposed. The human cost of the earlier prohibition became apparent in retrospect. Welders who'd injured themselves trying to maintain uphill technique in impossible positions had suffered needlessly. Ships that had required expensive repairs due to defects from rushed uphill welding had wasted resources and time. Most tragically, some of the structural failures that killed sailors might have been prevented if downhill welding's lower residual stress had been incorporated earlier. The Maritime Commission never publicly acknowledged these costs, but internal documents reveal that officials understood the implications. A memo from Admiral Emery Land to the Commission's chief engineer, dated September 1944 and declassified in 1978, stated bluntly, "We resisted a superior technique because it challenged our assumptions. That resistance had consequences we cannot undo, but must never repeat." William Francis continued welding at Moore Dry Dock through the war's end, completing his work on approximately 63 Liberty and Victory ships. He received no special recognition, no medal, no public acknowledgement that his forbidden technique had transformed an industry. His personnel file, preserved in the National Archives, contains a single notable entry from Theodore Palmer dated December 1944, a full year after the testing program that vindicated Francis's methods. The notation reads simply, "This welder's contributions to improved construction techniques have been significant. His willingness to question approved procedures when observation suggested better approaches exemplifies the innovative thinking necessary for continued progress." The post-war evolution of welding standards demonstrated how thoroughly Francis's rebellion had reshaped industrial practice. The American Welding Society, which published the structural welding code that governed everything from bridges to pressure vessels, incorporated downhill technique as an approved method in their 1947 edition. The code's introduction acknowledged explicitly that wartime maritime construction had proven the effectiveness of techniques previously considered unsuitable for critical applications. Pipeline construction, ironically the industry where Francis had learned downhill welding, adopted refined versions of the techniques developed in Liberty ship production. By the 1950s, oil and gas pipelines across North America were being welded using methods that traced directly back to Hull 473's controversial bulkhead seams. International maritime construction absorbed the lessons more slowly. British shipyards, proud of centuries of naval tradition, resisted downhill welding until competitive pressure from American yards forced modernization in the 1950s. Japanese shipbuilders, reconstructing their industry after the war's devastation, studied American Liberty ship construction extensively and incorporated downhill technique from the beginning of their rebuilding program. By 1960, the Japanese maritime industry had surpassed American production using methods that Henry Kaiser's workers had pioneered. The broader implications of the downhill welding controversy extended into industrial management theory and organizational behavior. Business schools teaching operations management used the Liberty ship welding story as a case study in the dangers of procedural rigidity. Harvard Business School professor Michael Porter, analyzing American industrial competitiveness in the 1980s, identified the Maritime Commission's initial resistance to downhill welding as a classic example of competency traps, where organizations become so invested in existing capabilities that they resist superior alternatives, because those alternatives threaten established expertise. The story illustrated a profound truth about innovation in complex systems. Breakthrough improvements often come from outside established industries, precisely because outsiders aren't constrained by that industry's assumptions. William Francis saw possibilities that maritime engineers missed because his frame of reference came from oil field pipeline construction, where different constraints produced different solutions. The Maritime Commission's experts weren't stupid or incompetent. They were trapped by expertise that had become dogma, by success that had calcified into inflexibility. Modern manufacturing philosophies embed this lesson in their core principles. Lean production methodology, developed by Toyota and adopted globally, emphasizes that workers closest to the actual process often understand it better than managers or engineers working from specifications. Six Sigma quality programs include formal processes for identifying and testing worker-suggested improvements. Total quality management treats frontline observations as valuable data rather than threats to engineering authority. These approaches all reflect the insight that Liberty ship construction demonstrated. The people doing the work sometimes know things that the people designing the work don't. The psychological dimension of the story deserves attention as well. Theodore Palmer's willingness to test Francis's forbidden technique rather than simply firing him represented unusual intellectual courage. Palmer had built his career on maritime expertise, acknowledging that an oil field welder might know something he didn't require, setting aside ego in favor of truth. Organizations rarely reward that kind of humility. Palmer received no promotion, no special recognition for the decision that ultimately improved Liberty ship construction. His reward was simply knowing he'd made the correct choice when institutional pressure pushed toward enforcing orthodoxy. The welders themselves, those hundreds of workers who quietly incorporated downhill technique before official approval, demonstrated their own form of courage. They risked termination by violating approved procedures. They trusted their observations and experience over written specifications backed by maritime authority. That trust required confidence that many workers lack, particularly women and minorities who'd been told repeatedly that they lacked the judgment to question expert opinion. Yet they questioned anyway, and their collective judgment proved correct. Constance Bowman's memoir captured this dynamic with particular clarity. She described a conversation with a male welder who'd trained in traditional shipyards before the war. He'd initially resented women entering the yards and dismissed their capabilities, but after watching Bowman complete a series of vertical seams using downhill technique in less than half the time his uphill methods required, he asked her to explain what she was doing. "I expected him to be angry or dismissive," Bowman wrote. Instead, he was curious. He wanted to understand why my way worked better. That conversation changed both of us. He learned a faster technique. I learned that even men who seemed hostile to women workers could set aside pride when confronted with better results. The war taught us all to value what worked over what tradition said should work. The statistical legacy of downhill welding's acceptance can be measured in the ships that survived. Liberty ships built primarily with uphill welding in 1942 and early 1943 showed structural failure rates of approximately 4.6% during their service lives. Ships built with significant downhill welding incorporation from mid-1943 onward showed failure rates of approximately 1.2%. The difference represented hundreds of avoided casualties, millions of tons of cargo delivered safely, and reduced repair costs that freed resources for other war production needs. The SS John W. Brown, one of two surviving operational Liberty ships and now a museum vessel in Baltimore, contains welds executed using both techniques. Sections built in the vessel's early construction phases show characteristic thick uphill weld beads. Later sections incorporate thinner, more uniform downhill welds. Maritime historians and welding engineers have studied the Brown extensively, and their analysis confirms what the wartime testing revealed. The downhill welds show less residual stress, better fatigue resistance, and fewer microscopic defects than uphill sections. After more than 80 years, the forbidden technique's superiority remains measurable in the metal itself. William Francis returned to Texas after the war, working in pipeline construction until his retirement in 1968. He died in 1976 in Houston, his obituary mentioning simply that he'd been a welder during the war. No mention of Liberty ships, no acknowledgement of the technique that transformed maritime construction, no recognition that his willingness to risk his job had improved an industry. The obscurity seems unjust until one considers how many similar stories remain hidden in industrial history, how many workers observed better methods but lacked Francis's courage to demonstrate them, how many improvements were lost because bureaucratic systems rejected innovations that challenged established procedures. The welding code revisions that incorporated downhill technique became Francis's permanent monument, though his name appears nowhere in those specifications. Every vertical weld executed using downhill progression in structures built since 1947 carries forward the principle he demonstrated in Hull 473's cargo hold. Every pipeline across frozen terrain, every skyscraper frame, every pressure vessel, every offshore platform, all of them potentially incorporate the technique that was forbidden until one welder proved it worked by doing it anyway. The Liberty ship program's willingness to eventually embrace downhill welding, despite initial resistance, distinguished American industrial culture from more rigid systems. German wartime production, by comparison, remained locked in engineering orthodoxy throughout the conflict. Specifications, once established, were rarely challenged regardless of operational results. The Kriegsmarine built submarines using welding procedures that German maritime authorities had approved in the 1930s, and those procedures remained unchanged even when better alternatives emerged. Japanese industrial practice similarly emphasized conformity to established standards over individual innovation. The Liberty ship program's ability to incorporate improvements from unexpected sources, even when those improvements contradicted official specifications, represented a cultural flexibility that contributed significantly to Allied victory. The time savings from downhill welding, multiplied across thousands of ships and millions of welds, translated into tangible military advantage. Every day saved in ship construction meant cargo delivered sooner, troops supplied faster, strategic initiatives enabled earlier. The cumulative effect of 15 to 20% faster welding on 60% of joints in each Liberty ship was measured not in hours, but in the operational tempo of global war. Ships arriving in theatre weeks earlier than scheduled altered battle timelines. Supplies delivered before critical shortages developed prevented operational failures. The strategic impact of a welding technique seems absurd until one considers the mathematics of total war logistics. Admiral Ernest King, Chief of Naval Operations during World War II, reflected on Liberty ship production in his post-war memoir published in 1952. He wrote, "The United States won the logistics war not through individual brilliance, but through systematic excellence, multiplied by industrial scale. Every small improvement in production efficiency, every day saved in construction time, every reduction in defect rates contributed to overwhelming material superiority. We didn't need perfect ships. We needed sufficient ships delivered fast enough that our supply chain never broke. The welding innovations that made Liberty ships faster to build and more reliable in service exemplified the industrial flexibility that totalitarian systems could not match. The forbidden technique that William Francis demonstrated, the method that Theodore Palmer had courage to test, the approach that hundreds of welders quietly adopted before official approval, represented something more significant than a manufacturing process improvement. It represented a principle about how progress happens in complex organizations. Innovation doesn't always come from research laboratories or engineering departments. It often emerges from practitioners who observe that official procedures don't match operational reality and who have the courage to demonstrate alternatives despite institutional resistance. Modern engineering education incorporates this lesson, though often without recognizing its origin. Students learning welding procedures in 21st century technical schools are taught both uphill and downhill technique as equally valid approaches for different applications. The controversy that nearly ended William Francis's career seems incomprehensible to instructors who've never known a time when downhill was forbidden. That generational amnesia is both the triumph and tragedy of successfully absorbed innovation. The technique is so thoroughly integrated into standard practice that its revolutionary origin is forgotten, along with the resistance it overcame. The workers who built Liberty ships understood something that engineers initially missed. They understood that procedures optimized for traditional construction didn't automatically apply to revolutionary assembly line production. They understood that gravity could be an ally rather than an obstacle if welding technique adapted to work with natural forces instead of fighting them. They understood that faster didn't necessarily mean inferior if the faster method was properly executed. These insights seem obvious in retrospect, but they required courage to act upon when official specifications said otherwise. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.